Hello, my name is William, and I will be bringing you through a detailed analysis of polylactic acid log pile scaffold use in bone tissue engineering. Despite the natural capacity of bone to heal itself, if an injury is greater than the critical size defect, then the bone cannot heal. Metallic implant devices can be used, however, they lack inherent biological activity. Typically, the body reacts by carrying out fibrous encapsulation. Autologous or allologous bone grafts can be used, however, they are expensive and can cause donor site morbidity. An alternative is to engineer an osteogenic scaffold. For scaffold design, the aim is to produce a scaffold that can modulate the process of healing while simultaneously providing mechanical support without igniting a stress shielding response from the body. The material should ideally degrade in parallel with the production of new bone matrix. The 3D printing method of fused deposition modeling was chosen for construction of our scaffold. In this method, the thermoplastic material is extrusion deposited in a layer-by-layer manner to give rise to the 3D structure. Polylactic acid, or PLA, was chosen as the thermoplastic material. PLA is a synthetic polymer which is both biocompatible and biodegradable, providing a controlled chemical breakdown. Steps in computer-aided design and printing, as well as subsequent compression and degradation analysis of the PLA scaffolds and solids, are outlined here. Computer-aided design of the scaffold is a very important step, as the chosen design has a large impact upon subsequent osteogenic and mechanical strength properties achieved. The better the construct design mimics the in vivo bone physiological conditions, then the better it will be for promoting osteogenesis. Uniaxial compression testing was performed upon the log pile PLA scaffolds and solid blocks using the Zwick biaxial tester. The effective compressive modulus of the scaffolds and solid PLA was calculated from the obtained force distance curves, with the scaffolds calculated to be 73 MPa. A degradation study of the PLA scaffolds and solids was performed by incubation in 20 ml of sodium hydroxide at 45 Celsius for 7 days. Scaffolds degraded to 36% of initial mass by day 7, while solids degrade to 52% of initial mass by day 7. From both visual and technical analysis, it is apparent that the PLA constructs display even surface erosion. Their matrix becomes thinner with time, but maintains its structural integrity. This even disintegration of the scaffold is facilitative of bone regeneration and vascularization in vivo. Due to a lack of micropores for use in self-sealing and the PLA lacking osteoinductive properties, the scaffold by itself is not suitable for in vitro use. However, its even degradation and porous structure make it suitable for use in vivo. The PLA scaffold perhaps has a low compressive modulus. This is typical, however, of synthetic polymers. While weaker than cortical bone, it is not to an excessive extent, and could perhaps still be of use for in vivo grafting.